Hello and welcome. In this video, we're going to take a look at another big theorem in vector calculus called Stokes Theorem. And it's actually quite related to Green's theorem. If we remember, with Green's theorem, it was a relationship between line integrals that unfortunately just had to exist on a plane and the area bounded by the curve. But now with Stokes theorem, we're going to extend that. So let's take a look. Green's theorem, once again, is where we have a vector field that is continuous and with continuous first order partial derivatives. And we have a positively oriented, simple closed, piecewise smooth plane curve, C. And it relates the line integral around the curve of f dot dr. That is just the tangential component of the vector field added up all the way around that closed curve. That is equal to the double integral of the partial derivative of q with respect to x minus the partial derivative of p with respect to y over the region D that is bounded by that curve. Well, now we're going to extend that. We're going to pretty well have the same kind of restrictions on our vector field and curve, with the exception that we're going to be looking at a space curve instead, though, where we don't have to stay to just a single plane. In a third dimension, we're going to be extending this to a curve that forms the boundary of some kind of surface. So we call it a boundary curve. Let's start off with some sort of oriented surface with a unit normal vector n hat. And then let's say that C is the curve formed by the boundary of that surface S. Now remember, we have an oriented surface and we also have curves with an orientation as well. We're going to assume that C is oriented by using the right-hand rule of that normal vector n hat. And just like with Green's theorem, this would mean that the area is on your left as you're traveling around the curve. So facing upwards with the normal vector pointing up here, you can see that we would have to have some sort of counterclockwise orientation for our curve when viewed from above the xy plane. With all of these criteria or hypotheses in place, we can establish Stokes theorem. Stokes theorem says that let's let S be an oriented piecewise smooth surface and let its boundary curve C be simple, closed, and piecewise smooth as well, with a positive orientation. Let's assume that F is continuous and that its first order partial derivatives are continuous over a region containing S and also C. Then the line integral of that boundary curve is actually equal to the surface integral of curl over the surface. Now, if you stop and think about this for a little bit, it's kind of an interesting relationship. Now, it's also very similar to Green's theorem, but we can even relate this all the way back to fundamental theorem of calculus. Because we have on the right-hand side, we're adding up the curl of a vector field, which is kind of like a form of a derivative, but for vector-valued functions. We're adding that over the entire surface, and we're saying that that is equivalent to just looking at the vector field itself, f, over the boundary. So you see that sort of relationship there? It's like if we want to integrate a function over an interval, then we just need to find an antiderivative and evaluate it at the endpoints. It's kind of similar here. The thing is that we're actually summing up the normal component of curl over the surface, and that is equal to the sum of the tangential component of the vector valued function f around the boundary curve. Now you'll notice how close Stokes' theorem is to Green's theorem. In fact, if we were to simplify this down to just being on a plane, then we could start off with a function which has a z component of 0 and a space curve with a z component of 0. If that's the case, then the surface that is being bounded by that curve would be on the xy plane and would have a normal vector of 0, 0, 1 pointing upward. If that is the case, then taking the dot product of curl f dot n hat is the same thing as curl f dot k. And since S is actually already on the xy plane, we don't even have to worry about finding its projection. The surface integral becomes a double integral already. And the z component of curl would be partial q with respect to x minus partial p with respect to y. And there we are. Stokes' theorem is a much more general form of Green's theorem, and Green's theorem is a special case of Stokes' theorem. Now, let's see where we can apply Stokes' theorem. Perhaps instead of calculating the line integral of a space curve, we might be able to come up with a surface that is bounded by that curve and use Stokes' theorem instead. In this example, let's take a look at the curve of intersection of a paraboloid and a plane. We've got the paraboloid opening downward, z equals 25 minus x squared minus y squared, and a horizontal plane, z equals 16, parallel to the xy plane. Let's suppose that the curve is oriented clockwise when we're viewing that from above the xy plane. And let's see if we can calculate the line integral of f, where f is the field x minus y, comma y squared, comma yz. Now the first thing we can do is we could just skip over Stokes' theorem entirely and just calculate this line integral directly. Now that is only going to be possible if we can find a parametrization of the curve, and in this case that might not be too terrible. The first step will be finding a parametrization. Now in this case we do know that this curve lies on the plane z equals 16, so we already know its z component. Now we need to find the curve of intersection of that plane and the paraboloid. So we'll set the two equations equal to each other. That gets us 16 equal to 25 minus x squared minus y squared, or x squared plus y squared equals 9, and that's a circle of radius 3 when projected down here onto the xy plane. So it's fairly easy to come up with a parametrization of a circle and just have the z component equal to 16. We have x equal to 3 cosine t, y equal to 3 sine t, and z equals 16 to get us a counterclockwise direction. And we can turn that into our parameterization r of t, and we're going to need the derivative of that. So we'll calculate that ahead of time before we start trying to evaluate the line integral. And remember that our parameter domain t will just be once around the circle from 0 to 2 pi. And let's see just how bad this integral might be without using Stokes' theorem. The first thing we'll have to do, remember, is to plug in our parameterization into the field. So that will end up being x minus y is now 3 cosine t minus 3 sine t. Y squared will be 9 sine squared t, and yz is going to be 21 sine t. We have to do the dot product of that and r prime. Okay, well, let's expand that out and see what we would be left with. That leaves us with a mess of products of sines and cosines. Not great, but not terrible. I'm sure that we could use a couple integration tricks to come up with an actual value for this. Well, of course, we could always factor out 9 and then use some trigonometric identities. But let's take a look at our other options. In fact, there are two surfaces that will have this boundary curve. And maybe let's take a look and see what these surfaces look like in Maple. All right, I've plotted these as well as the vector field in Maple. And you can see the curve of intersection there was that red circle, just at z equals 16 and a radius of 3. Now that curve there is a boundary curve of two different surfaces. We actually have a paraboloid that you can see just poking out the top there, which must have to have an upward normal vector to match the direction of travel along that curve. And also we have this plane, and that would form just a circular disk. And it would also have to have an upward normal in order for us to have a counterclockwise orientation of the curve. So let's see if we can take a look at the flux integrals of the curl of this vector field over those two surfaces. Now let's start off with the paraboloid first. Now to use Stokes' theorem, there's a couple things we're going to have to calculate. First of all, we're going to need to find the curl of this vector field. And secondly, we're going to need to find out what our normal vector is that's pointing upward so that we can take a look at turning this surface integral from Stokes' theorem into a double integral. Let's start off with curl. Remember that curl is the cross product of our vector differentiation operator and the vector field, x minus y, y squared, and yz. So taking a look at that cross product, you're going to find out that a lot of these partial derivatives are actually equal to 0. The partial derivative of yz with respect to y is z, but the partial derivative of y squared with respect to z is 0. So that gives us our first component, z. And you're going to see very nice partial derivatives will give us a curl vector that's pretty straightforward. It's just z, comma 0, comma 1. So far things are looking up a little bit. Let's take a look at our surface now. We don't necessarily have to come up with an overly elaborate parametrization for this surface since it's already a function. Z equals g of xy, the function 25 minus x squared minus y squared. And since we need an upward pointing normal to match the orientation of our curve of intersection, we're going to use negative partial gx, negative partial gy, comma 1. And that's just simply 2x, 2y, and 1. Now we're ready to use Stokes' theorem. Our line integral can be replaced with a surface integral of curl f. So let's start by plugging in curl of f. Now, in this case, curl, since it is z, 0, 1, when we turn this into a double integral over a region in the xy plane, we're going to have to plug in z equals 25 minus x squared minus y squared. After plugging that in, we can take the dot product with 2x, 2y, and 1, and now we have a double integral. Now remember that D is the region that we get by projecting this part of the paraboloid onto the xy plane. Now we've already seen the curve of intersection, so we already know that D is just a circular disk of radius 3 centered at the origin. Okay, well how bad is that going to be to integrate? Maybe we should try expanding that out first. After expanding the dot product, we have 50x minus 2x cubed minus 2xy squared plus 1. Now, as you can probably guess, since we're integrating over a circle centered at the origin, it's probably best to convert to polar coordinates. That's not going to be terrible for the region, but if you take a look at this function and we make all of the substitutions with x equals r cosine theta and y equals r sine theta, again, we're going to be stuck with a big mess of products of sines and cosines. So maybe this isn't the easiest method yet. Why don't we take a look at that other surface that forms the curve of intersection, and that's simply just a plane. And let's call the plane S2. Luckily, we don't have to recalculate curl. It's still going to be z, 0, 1. And this time around, our upward normal vector is going to be even easier to calculate. Since our function, z equals g of xy, is simply just 16, our upward normal is simply k. It is the vector 0, 0, 1, or k hat. That makes trying to look at this surface integral probably the easiest one yet. We get to repeat the same couple steps initially as in surface S1, which was the paraboloid. Only this time, when we change to a double integral, we're going to be looking at a much easier dot product, and we only have to substitute z equals 16 into our vector field. Well, you couldn't end up with a much better dot product than that. 16, 0, 1, dot product with 0, 0, 1. That's just simply equal to 1. Well, that's always really nice. We're just integrating a double integral of the function 1. Remember that that's nothing more than actually just calculating the area of that region. And once again, D is the circular disk of radius 3 centered at the origin. We already know how to calculate the area of that circular disk. It's just pi r squared, which gives us 9 pi. Now, we could have probably used any one of these integrals and been able to calculate the result by hand. It's just that some of them would have taken more work than others. So why don't we check and see that they all come out with the same result, 9 pi, by just going to Maple and letting it do most of the work. So here again, I've got that surface, and you can see the paraboloid, I've got the plane, I've got my vector field, and I've got the curve of intersection there. And I'm just going to scroll down here and show you. We've got the line integral of that path from t equals 0 to 2 pi. That integral should turn out as 9 pi. I've got a flux integral that's just looking at the curl over the surface. And here's the parametrization form of it. X equals x, y equals y, z equals 25 minus x squared minus y squared. And using the parameter domain where x and y are in the circle of radius 3 at the origin. You see 9 pi. And just to check our own answer, here's that other surface where z is equal to 16. And again, the region is over a circle at the origin of radius 3, and that also ends up as 9 pi. So luckily, all three of these agree, and we've confirmed Stokes' theorem for this particular problem. That's not to say we've proven Stokes' theorem, but it definitely seems to be true for this particular example. Why don't we take a look at one other application of Stokes' theorem? In this application, let's think about taking a particle and moving it along a path consisting of 3 vertices, 2 0, 4, 4, 0, 2, 2, 3, 10, and then back to 2, 0, 4. So it completes a complete closed loop, and let's say it goes in a counterclockwise direction when viewed from above. Now we have a force field here, x squared y, comma y plus 6z, comma yz, and let's see how much work is done by that force to move this particle around that path. Now, of course, the first option is just calculating work in the conventional sense, where we look at the line integral of that force field over the closed path. Now, I know I'd rather probably not use that method since I'm going to have 3 separate line segments from the point 204 to the point 402, from 402 to 2310, and from 2310 back to 204. And that's going to be 3 separate curves, C1, C2, and C3. So I'll have to calculate work separately and add them together, and that's not exactly efficient. So why don't we use Stokes' theorem on the actual triangular surface itself? And let's just use a nice conventional plane, since we often see that as being the easiest surface to work with. Using Stokes' theorem, first of all, we're going to have to calculate the curl of that vector field. And once again, using our cross product of the vector differentiation operator and the field, we actually end up getting a fairly nice looking curl vector, z minus 6 comma 0 comma negative x squared. But we still need to figure out what this surface is. And let's say that all 3 of these points are just going to lie on some plane. And we'll need to find out what the equation of that plane is. Now, it's actually fairly easy to look at the partial derivatives if we are just simply taking a look at 2 consecutive points. From 204 to 402, well, that's pretty handy. That is just moving 2 units in the x direction and moving 2 units down in the z direction. So if we wish to have our surface in the form z equals g of x comma y, then we already know that the partial derivative gx is going to be negative 2 over 2, or a partial derivative of minus 1. That's pretty handy. And actually, we also see a point 204 and a point 2310, which is a change of y of 3 units and a change of z of 6 units. So we can also calculate that partial derivative in the conventional form of calculating slope. That would tell us that the partial derivative of g with respect to y is 6 over 3, which is equal to 2. And actually, now that we know the partial derivatives gx and gy, we can already get an upward normal since this is a plane. And it gives us the upward normal of 1 comma negative 2 comma 1. And since this is a plane, it's going to have the same normal vector at every point on the triangle. Let's see if we can come up with the equation of the plane. We're going to need that in order to get our z in our curl vector replaced with some function of x and y. Now, we could use any of the points, but let's use one of the points like 204. And to get the equation of a plane, we'll take a normal vector and we'll dot product that with x minus x naught, y minus y naught, and z minus z naught, and set that equal to 0. So there's our 204, and we can expand that out and solve for z in order to get this in the form of a function. That gives us z equal to 6 minus x plus 2y. And that's our function g of x, y. All right, let's apply Stokes' theorem now. The work done by our force field F to move the particle around that closed path C is really just the surface integral over this triangular region of the curl of that force field. Since we've calculated the curl vector, we can plug that in. And this is where we will need to know that z is equal to 6 minus x plus 2y, so that we can plug that in to curl and turn this into a double integral over a region on the xy plane. Turning this into a double integral, z minus 6 is equal to negative x plus 2y, the 6's cancel. We have 0, comma negative x squared, and we're going to dot product that with our upward normal 1 minus 2, 1. Let's expand that out and see how much this simplifies first. This gives a double integral of minus x plus 2y minus x squared dA. At this point in time, we're going to have to take that triangular region and project it onto the xy plane to figure out what we can do to turn this double integral into an iterated integral. It's fairly easy to see that a triangular region in 3-dimensional space, when projected onto the xy plane, is going to be a triangle. We just need to set all of the z components equal to 0, and we can project them straight down. This gives us the points 2, 0, 4, 0, and 2, 3. And this is a fairly simple region to either iterate in the form of dy dx or dx dy, but I'm going to just choose to use dy dx because I typically like to have functions of the form y equals a function of x. So let's start with the boundaries on x. X goes from 2 to 4, and then find those functions for y. At any point between 2 and 4, our bottom boundary for y is y equal to 0. And our top boundary will be this diagonal line. We can calculate the slope of that line, since you can see it's got a rise of -3 for every run of 2. It's got a slope of -3/2. And what about its y-intercept? Well, we could just really make this easy and trace that line back 2 more units, and that would go up by another 3 units to get us a y-intercept of 6. Okay, now that we've got those boundaries, y is going to go from 0 to -3/2 plus 6. At this point in time, we can turn this into an iterated integral. Putting those boundaries onto our double integral, we have an iterated integral dy dx, and we'll integrate with respect to y first. That gets us -xy plus y squared minus x squared y, evaluated from y equals 0 to y equals -3/2x plus 6. One of the endpoints of this interval is y equal 0. So we just need to plug in y equals -3/2x plus 6 and expand this out. And of course, it's going to cause a little bit of a mess when we can try collecting some terms here, and hopefully it's not terrible. Once we have collected terms, we have 3/2x cubed minus 9/4x squared minus 24x plus 36. We're ready to integrate with respect to x now. And that gets us 3/8 x to the 4 minus 3/4 x cubed minus 12x squared plus 36x. Now, all of these fractions are actually going to nicely cancel out when we plug in 4 and 2. Hopefully we just get a nice whole number out of this. And in fact, the work done by this force is -24. Now remember, it's quite okay for us to have a negative answer here. This is in terms of a physical application, talking about work done by that force. And well, force has got a direction, and it seems like it's probably pointing in the opposite direction to our direction of travel. We are trying to complete this triangular path, but the force is working against us. So it's doing negative work, and in order for this particle to be moving in that path, we have to put in a lot of work to complete that. It gives us kind of this idea of circulation. If this was some sort of fluid and not a force field, then our particle would probably want to go the opposite way around that triangle instead of the direction we're talking about going counterclockwise. It may be worthwhile to actually take a look back and see how much work is done by that force on each of the line segments. Some of the line segments could be positive work, but overall, when we add them together, we end up getting negative work done by the force. And there we are. That's kind of a nice application of Stokes' theorem. It's just, you can see how talking about the boundary curve or talking about the surface, they are interchangeable. And the work done to move a particle around that path can be related to looking at the sum of the normal components of curl over the oriented surface bounded by that curve. So it's, again, this relationship of sort of this interior region, which is the surface, and the exterior, which is the boundary curve. So it's kind of another one of those fundamental theorem of calculus moments. Now we'll take a look at some other applications with curl in the future, but we'll save that for later. Thanks for watching, and I'll see you in the next video.